What is mechanical energy? Mechanical energy is basically a form of energy that can be converted to mechanical work completely and directly by an ideal mechanical device. So mechanical energy is energy that can be converted to mechanical work completely and directly by an ideal mechanical device. And so what this means is a good example of an ideal mechanical device would be, say, an ideal pump or an ideal turbine. And ideal means that it doesn't have any friction or any other types of losses. So basically what this means is that, well, first of all, what isn't mechanical energy? So thermal energy is not mechanical energy. So thermal energy is not mechanical energy. And this is because thermal energy can't be converted to work directly and completely. And this is basically stated in the second law of thermodynamics. So what does a pump and a turbine do? Well, a pump basically transfers mechanical energy to the fluid by raising its pressure. So a pump raises a fluid's pressure, and when the fluid's pressure is raised, that is transferring energy to the fluid. A turbine does the opposite. A turbine drops the pressure, so drops the fluid pressure. And when it does this, it's basically extracting mechanical energy from the fluid. So I'm just going to put that it extracts mechanical energy from the fluid. And then on the pump, I'm going to put that this transfers mechanical energy to the fluid. Before writing an equation for the mechanical energy of the flowing fluid, let's first look at a couple of things. So, first of all, let's look at the pressure. So the pressure is not within itself energy, but the pressure of a flowing fluid is associated with its mechanical energy. So I'm just going to actually go to the next slide. So pressure itself is not an energy, but pressure of a flowing fluid is associated with its mechanical energy. So let's look at pressure units. So let's look at Pascal. Pascal is equivalent to Newton per meter squared, and this can be written as Newton meter per meter cubed. So this Newton is a unit of force, and the Newton meter is equivalent to a joule, which is a unit of energy. So with the Newton meter, we have a force times a distance, which is work, and that's unit of energy. and we still have the meter cubed. So what we have is a unit of energy over a volume. We've seen that the pressure unit can be seen as a unit of energy per volume. So then let's look at this PV. So this is the product of the pressure and the specific volume. And this is equivalent to P over rho. And the reason why is because this has units of joules per kilogram. And if we look at this PV, this is the specific volume. So this specific volume has units of volume over mass. And so this, if we have P over and then rho is mass over volume, and so the volume will come up here. So this PV and P over rho are equivalent. And this has units of joules per kilogram, so this is energy per unit mass. This is the pressure force acting on a fluid through a distance per unit mass. So this is the pressure force acting on a fluid through distance. So this is this Newton meter, or like the pressure times the distance. So pressure force acting on a fluid through a distance per unit mass. So that would be this P over rho. So the flow work, so this is called the flow work. I'm just going to circle this. So this is the flow work. This is viewed as part of the energy of a flowing fluid. So this flow work is part of the energy of a flowing fluid. And so this is often called the flow energy. So now let's look at the mechanical energy of a flowing fluid. The mechanical energy of a flowing fluid is equal to the flow energy, so P over rho, plus the kinetic energy, so V squared over 2, plus the potential energy. So this is the potential energy, the kinetic energy, and this is the flow energy. And this can be written in rate form as E mech is equal to the mass flow rate multiplied by E mech. So this is equal to the mass flow rate multiplied by P over rho plus V2 or V squared over 2 plus GZ. And this m dot is the mass flow rate of the fluid. So this dot over the variables just means that this is rate form, and so what that means is that it's per a time. So for instance, this E mech might be joules per second, and this m dot might be kilograms per second. So then what we can do is we can write the mechanical energy change of fluid during incompressible flow. So delta E mech is equal to P2 minus P1 over rho plus V2 squared minus V1 squared over 2 plus G Z2 minus Z1. And this has units of kilojoules per kilogram. So this is lowercase because it's on a unit mass basis. So I'm just going to say it's per kilogram. And just to specify this is only valid for incompressible flow. And what that means is that your density is constant. So if your density changes, you're going to need to find a relationship between your pressure and your density. So what we can get from this equation is that the mechanical energy doesn't change during the flow if the pressure, density, velocity, or elevation remain constant. So in other words, if P2 and P1, if P2 and P1 are constant, so they're the same, then P2 minus P1 is 0. If V2 and V1 are constant, that means that V2 squared minus V1 squared is 0. And if Z2 and Z1 are constant, that means that Z2 minus Z1 is 0. And so if all of these terms are 0, that means that your mechanical energy will be 0. So that means that, or your change in mechanical energy will be 0. So that means that your mechanical energy doesn't change if the density, velocity, pressure, and elevation remain constant. And so if these are constant, then this is 0. If this isn't 0, so let's say that the change in mechanical energy is greater than 0, this means that the energy is supplied to the fluid. So this would be like a pump. So a pump is supplying energy to the fluid and increasing the pressure. If delta E mech is less, if the change in mechanical energy is less than 0, that means that energy is extracted from the fluid. So this would be like a turbine. It lowers the pressure of the fluid and extracts energy from the fluid. So we can write an equation for the maximum work that we can perform. So the maximum work is equal to the mass flow rate multiplied by the change in mechanical energy of the fluid. And this max is referring to an ideal device. So an ideal device. So this would be like a turbine or a pump with no friction. So in other words, it has no losses. It's ideal. So let's look at an example of how we would calculate this maximum work from the mechanical energy. So let's say that we have a turbine, and so let's say that we have a lake here that has some elevation. So we have water here, and this water can flow through this dam, and then let's say that we have water down here as well. And when it flows through this dam, it's going to flow through a turbine. So we have a turbine here. And let's say that this turbine is connected to a generator. So the turbine is turning a shaft that's connected to a generator, and then that generator is going to generate electricity. And let's say that this water has a height, so the water at the top of the dam has a height of h. So what we need to do in order to evaluate this, we need to look at where we're we need to figure out what our reference points are. So I'm going to say our reference point is right here. So at the water surface at the top of the dam. And then the second reference point is here at the water surface at the bottom of the dam. And we want to calculate the maximum work that we can get from this turbine. So the maximum work is equal to the mass flow rate multiplied by the change in mechanical energy. So this is equal to the maximum flow rate, the mass flow rate, multiplied by P2 minus P1. And remember, so let's write down what our assumptions are. So we're assuming no friction. We're also assuming that this is incompressible flow. So in other words, the density is constant. So I was going to put rho as constant. And so when you're using these equations, you always want to specify what your assumptions are, because if you have an assumption, like if you have something that doesn't apply, so for instance, let's say that our density isn't constant, so we don't have incompressible flow, that means that we wouldn't be able to use this specific equation that I'm writing. So we need to specify that we have incompressible flow so we know that this equation applies. So this is P2 minus P1 over rho plus V2 squared minus V1 squared over 2 plus G Z2 minus Z1. Now let's look at this equation. So we have our reference point. First let's look at the pressures. So P1 right here, this is atmospheric, and P2 right here, this is also atmospheric. So that means that P2 minus P1 is 0. So we can say this term is 0. And we're also going to assume that the water here, so the water right here at 1 is, like, the velocity is pretty low or pretty much 0. And then we're going to assume that the water here, the velocity is also pretty low, so pretty much 0. So V2 squared minus V1 squared is 0. So we can rewrite this equation as the work max is equal to the mass flow rate multiplied by G, and then Z2 minus Z1 is just H, the height. So this is the maximum work from the system. So now let's look at something. What if we had have specified our reference points as right here and right here? So let's rewrite our equation. So the maximum work is equal to the mass flow rate multiplied by delta E mechanical. So mechanical energy. There should be an E right there. So this is equal to the mass flow rate multiplied by P2 minus P1 over rho plus V2 squared minus V1 squared over 2 plus G Z Z2 minus Z1. All right, so first of all, the pressure here at point 1 and the pressure at point 2 are different because we know that there's going to be a pressure drop in this turbine. So the turbine is going to drop the pressure. So that means that P2 minus P1 is no longer 0. We can assume that the velocity here and the velocity here, so I'm going to put V1 and V2. So we can assume that those two velocities are the same. Otherwise, we would be increasing the water in our turbine over time, which it's not. So that means that if the velocity at V2 and V1 are the same, that means that V2 squared minus V1 squared is 0. And we can also assume that this height, so from 1 to 2, is approximately the same. So that means that z2 minus z1 is 0. So in this case, the maximum work is equal to the mass flow rate multiplied by delta E mech, which is equal to the mass flow rate. And in this case, it's equal to the change in pressure over rho. So depending on where we defined our reference points, we ended up with a different equation for calculating the work. But these two, if we had some numbers to plug into these equations, we should end up with the same answers. So when you set up these problems, you want to set your reference, first of all, you want to specify where your reference points are, because you can see that depending on where our reference points were, we ended up with a different equation, but we should end up with the same result from both of them. So when you set up your problem, you want to specify where your reference points are based on the information you have. So if you're given the height, then you would want to put your reference points at the top and the bottom of the height. If you're given, say, the pressure drop across the turbine, then you would want to specify your reference points across the turbine. And the same thing with a pump. Let's say this were opposite and we were pumping water to the top of this dam. If we're given the height that we're pumping the water, then we would want to specify our reference points at the top and bottom of the dam. But if we were given the pressure increase across the pump, then we would want to specify our reference points on either side of the pump. And so when you're doing these problems, you want to start with the full equation for the mechanical energy. And then you just want to go through and figure out, okay, is P2 minus P1 over rho 0 or not? Is V2 squared minus V1 squared over 2? Is your kinetic energies, is your change in kinetic energy 0 or not? Is your change in potential energy 0 or not? You might have some cases where the change in kinetic energy and the change in potential energy aren't 0, and so you would need to calculate those for both cases. So that would be if your velocity, like say you have water flowing over a dam, and so you have a change in potential energy, but let's say that your velocity is also changing, so then you have a change in kinetic energy. So always start with this equation, specify where your reference points are, because you can see how you end up with different results depending on where your reference is, and then go through and figure out which terms are 0 depending on your reference points, and then solve from there.